Hello, let me introduce our paper, Progressive Proxy Anchor Propagation for Unsupervised Semantic Segmentation. Semantic segmentation is a major task for various fields, including robotics and autonomous driving. However, existing supervised approaches demand extensive pixel-level annotations. So it has spurred the emergence of unsupervised semantic segmentation, which is to capture pixel-level semantics of all things and stuff with unlabeled data. In recent, as discovering pixel-level semantics from scratch is challenging, several works train the segmentation head guided by the image-level self-supervised pre-trained model, such as Dino. It can provide a proper pseudo-labels to train the segmentation head because it provides high-quality general representation. Most recently, HP discovers pseudo-positives from nearest neighbors of each anchor to leverage contrastive learning. However, they exclusively rely on the similarity metric on a per-patch basis within an imperfect embedding learned in an unsupervised manner at the image level. Consequently, we point out their limitation that there are numerous false positives in both the positive and negative sets. So, we address this by establishing a reliable proxy anchor to gather more trustworthy positive and negative sets. In specific, we relocate each anchor's proxy to densely populated regions of semantically similar samples, identifying more trustworthy positives and excluding ambiguous samples from training. Here, the proxy anchor indicates the relocated anchor. Like the existing methods, we utilize Dino to make pseudo-supervision and fine-tune a VIT model initialized with Dino. To train the model, we provide contrastive learning-based algorithm using pseudo-supervision obtained through our progressive proxy anchor propagation. Let me show you the detailed process of progressive proxy anchor propagation algorithm. We begin by defining a tight boundary around each anchor to construct a small, reliable positive set. This is because the samples within closely adjacent regions are highly likely to share similar semantics even within the image-level pre-trained embedding space. Subsequently, we iteratively undertake the two steps to enlarge a trustworthy positive set per anchor. For the first step, we redefine the position of the proxy anchor based on the distribution of identified positive samples. Secondly, we expand the positiveness boundary according to the reliability of the new proxy anchor position. This iterative process enables collecting a large number of trustworthy positive patches. Yet, we notice that the positiveness boundary might not be a perfect measure to detect all the positive samples. In other words, there exists a degree of ambiguity around the boundary where both positive and negative instances might coexist. To address this, we define an ambiguous set for each anchor which is excluded from the contrastive loss. Like the way for defining the degree of positive expansion, the size of ambiguous set is determined based on the reliability of the relocated proxy anchor. Consequently, while utilizing the positive and negative sets in contrastive learning, we disregard the ambiguous set. This approach effectively eliminates potential false positives in the negative set. Overall, we construct contrastive loss based on the trustworthy positive set and ambiguity excluded negative set to train the model. These are the experimental result tables with 4 datasets. As can be seen here, our proposed model provides consistent performance improvements over the previous SOTA models, especially in the large-scale dataset ImageNet-S. To verify the qualitative results, we plot simple to complicated scenes in order from left to right. We can observe that our PPAP shows consistent performance improvements. Thank you.